Okay, welcome everybody to Math 40. This is week 7 and we are starting a new unit on graphing the trigonometric functions. So if you haven't done so already, I encourage you to print these set of lecture notes, which should appear on Canvas under Unit 3. So let's go ahead and get started. So page 1 deals with basic graphs and particularly the graph of sine of x. Now I want you to think back when you were learning how to graph any equation, maybe y equals x plus 1. The first method that you were ever introduced to was plotting points. So that is considering some x values, plugging them into the equation, seeing what the corresponding y value was, and then plotting that point x comma y. So we're going to do exactly that same procedure with the table of points for sine. And as you can see on this table, we have already been given a set of x values that we should be plugging in. So for x is equal to 0, if we plug it into f of x is equal to sine of x, we're going to get f of 0 is sine of 0. And you can take a look at the unit circle. Sine of 0 is 0. So we actually get the ordered pair 0, 0. So one of the points will be at the origin for sine of x. Okay, next we have pi over 4. So f of pi over 4 means we're trying to evaluate sine of pi over 4. And sine of pi over 4, again, if you take a look at the unit circle, we'll see that that is radical 2 over 2. Now radical 2 over 2, on the calculator, if we punch it in, let's see what number it gives us so that we're able to better plot it on the graph. I think I have one too many. There we go. So it's about 0.7. Okay, this is about 0.7. So that means that I'm going to be plotting the point pi over 4, comma 0.7, where this is an approximation, so it's not exact. Now, as you can see on the x-axis, we don't have pi over 4 explicitly. The intervals are step sizes of pi over 2, so we have the first tick mark at pi over 2, then at pi, then 3 pi over 2, so on and so forth. So in order to figure out where is pi over 2 on our x-axis, we can take pi over 2 and divide by 2, and that'll give us the pi over 4. So halfway between 0 and pi over 2 would be here. So that means that pi over 4 is at that point. Again, if you're wondering, if you're a little confused as to why, we'll just consider this. Half of pi over 2, okay, so remember half of, that keyword of means multiplication. So half of pi over 2 means we multiply across numerator and across denominators, and we get a pi over 4. So pi over 4 is half of pi over 2. That means that we take this interval, cut it in half, and then get the location of pi over 4. Okay. And just because we are going to be needing other multiples of pi over 4, let's go ahead and label the rest of tick marks on the x-axis, and then we'll continue to find the ordered pairs. So we have pi over 4, this is 1 pi over 4, this is like a 2 pi over 4, right? 2 times pi over 4. Then that means that the next one would be a 3 pi over 4. After that, we would have a 4 pi over 4, which is simply pi. Then we can have a 5 pi over 4. This is the same as a 6 pi over 4. Followed by 7 pi over 4. And finally, that last tick mark would be 8 pi over 4. But all of these even numerators can be simplified, can be written in lowest terms to the numbers that actually appear on the tick marks. Okay, so now that we have that labeled, we can go ahead and estimate where is going to be the point pi over 4 comma 0.7. So here's pi over 4. This would be 0.5. So 0.7, I'm going to estimate, is about there. Okay, next one, pi over 2. f of pi over 2 means that we have sine of pi over 2. Now again, you can look at the unit circle to help you identify what is sine of pi over 2. You also have your calculator handy, so you can always punch in these numbers. So for instance, if I do sine of pi over 2, making sure that I'm in radian mode now, this is given in radians, that is going to give me a 1. So sine of pi over 2 is 1. Plotting the point pi over 2 comma 1 brings us to that point there. Now, f of 3 pi over 4 means we're evaluating sine of 3 pi over 4. Again, you can use the unit circle. If you look at the unit circle, you're going to get that this is radical 2 over 2. If you use your calculator to help you out, then you're going to get that it's approximately 0.7, which is the same thing as radical 2 over 2. So we're going to get a 3 pi over 4, comma 0.7, where this is an approximation. So we'll have a point that is on the same level, on the same horizontal line. And like if we imagine a horizontal line passing through this first point, it's also going to pass through the second point at 3 pi over 4. Okay, then f of pi means we're evaluating sine of pi. Sine of pi is going to be 0. Again, you can look at the unit circle or use your calculator for that. We'll have pi comma 0, which is that point. F of 5 pi over 4 means we're evaluating sine of 5 pi over 4. Let's look at our calculator. Sine of 5 pi over 4 is going to give us a negative 0.7 this time, which means this is actually negative radical 2 over 2. Okay, so we're plotting the point 5 pi over 4, comma, negative 0.7 approximately. Okay, so here is 5 pi over 4. This halfway between 0 and negative 1 would be negative 0.5. So that means that at 5 pi over 4, we have approximately negative 0.7. Okay, then 3 pi over 2, we'll just repeat the same process, plug in to sine, see what the value is, and then plot the points. This is going to be a negative 1. Again, use either calculator or unit circle to verify, which means that we'll have a 3 pi over 2 comma negative 1. That is this point down here. At 7 pi over 4, we're going to get a, well, let's see, let's use our calculator to help us out. I'm going to change that 5 to 7. We get a negative 0.7. So this is actually negative radical 2 over 2, which is approximately negative 0.7. So we'll get a 7 pi over 4, comma negative 0.7. So again, we're coming back up towards the x-axis. And then our last point, 2 pi. F of 2 pi means we're looking at sine of 2 pi, and that is 0. So we have the point 2 pi, comma 0. Okay. Well, now if I draw a line connecting all of those points, I see that we don't have a straight line, right? We have this curve that initially starts going up, it reaches a maximum of 1, and then starts coming back down towards 0, and it doesn't stop there, it continues to decrease all the way down to negative 1, and then comes back up, back to 0 at 2 pi. And so that is how sine of x is going to look like for the range, or over the range 0 to 2 pi. That means if you remember on the cycle, 0 to 2 pi completes one, on the unit circle, 0 to 2 pi completes one cycle. So what we're looking at is one complete cycle of sine of x. Let's compare the graph of sine of x with the unit circle. So here I have the unit circle that we worked on a few weeks ago. And I want to compare what happens to the graph versus what's happening on the unit circle. So on the graph, if I consider an angle that measures 0 radians, I get a sine that has a value of 0. Okay, so again, 0 radians would mean the angle has initial side on the positive x-axis and the terminal side doesn't open, right? So it remains there. The corresponding point to that terminal side would be 1, 0, and to obtain the sine, we always look at the y-coordinate, which is the 0. Okay, so those 2 points agree there. Then we start increasing to pi over 4, the angle pi over 4. So that's here on the graph. At pi over 4, we got radical 2 over 2, which we approximated to 0.7. So we're at that point. And here is the sine of pi over 4, which is radical 2 over 2. Then as the angle continues to increase, notice sine reaches 1, which corresponds to this peak on the graph. From there, we start decreasing. So from there at 3 pi over 4, we reach 0.7, which is radical 2 over 2 on the unit circle. Then as we go down to pi radians, we reach a sine of 0 again. Okay, then we continue to go open a larger angle to 5 pi over 4. And at 5 pi over 4, we have negative radical 2 over 2, which is about negative 0.7, and that corresponds to this y value down here of negative 0.7. And then we go to 3 pi over 2, so an angle that measures 3 pi over 2. That has a y value of negative 1, which means that the sine is negative 1. And that is pretty much the lowest number it can reach. The smallest number it can reach is negative 1. After that, the angle starts to, it's still increasing, but the y value starts to increase for every point on the terminal side, right? We go to negative radical 3 over 2, negative radical 2 over 2 at 7 pi over 4, which corresponds to this point on the graph, and then it makes it back up to a y value of 0 at 2 pi, which corresponds to this point here. So that is the behavior that we're seeing then on the graph. We see numbers increasing to 1, then back down to 0, down to negative 1, and then back up to 0. Okay, so that is the relationship between the sine graph and the values that we see on the unit circle. And so with that idea in mind, I want us to extend the sine graph beyond 0 to 2 pi. Okay. So first what we'll do is we'll go ahead and transfer over what we found for the graph in this interval, which is one cycle. And so basically what we saw is that at 0 we had 0, at pi over 2 we reached 1, at pi we reached 0, at 3 pi over 2 we reached negative 1, and at 2 pi we reached 0. The tick marks in between represent the pi over 4, 3 pi over 4, so on and so forth. And I know that at those points I reach about 0.7, so I'm going to say that is about, that's about there. And so that's the one cycle from the from page 1. Now if we want to extend, let's say to the right, okay, what's going to happen? And let me label tick marks. So this was pi over 4. Then this is 2 pi over 4. Next would be 3 pi over 4. This is 4 pi over 4. So then we have 5 pi over 4. This is 6 pi over 4 and 7 pi over 4. This would be 8 pi over 4, so this is 9 pi over 4, 10 pi, 11 pi, and 12 pi over 4. So what happens at 9 pi over 4? Well, again, let's consider the unit circle. So here's the unit circle. Let's say that we have an angle, and this is going to represent my terminal side. So we have an angle that is going to open 2 pi radians, meaning it's going to complete the cycle. And then after that, it is going to complete pi over 4 more radians. Okay, so that is what's happening here in the graph. We complete the 2 pi radians, and then pi over 4 more, remember, because the distance between any two tick marks on the x-axis is pi over 4. Right, so if I take, sorry, that should have been a 4. If I take 2 pi and I add a pi over 4, I'm going to get 9 pi over 4. So what happens at that point? What happens at 9 pi over 4? Well, I get a y value of radical 2 over 2, so that means that sine of 9 pi over 4 is going to be radical 2 over 2. So I see that the values are going to start to repeat, meaning here I'll have the same point that I had at pi over 4, because those two angles are coterminal, right? So we're going to get the same y value of 0.7 approximately. If we then want to take a look at what happens at 5 pi over 2, well, 5 pi over 2, we said that is completing 2 pi radians and pi over 2 more radians. This is 2 times pi over 4, so this is pi over 2 more radians. And so what happens is we're completing the cycle, and then after we complete, we stop at 3 pi over 2 radians more, at pi over 2 radians more. So that means that we get an angle that is coterminal to pi over 2 with a y value of 1. So that means that sine is 1. So all of these points are repeating. 5 pi over 2 corresponds with what happens at pi over 2. And at 11 pi over 2, we're going to repeat what happened at 3 pi over 4. At 3 pi, we're going to repeat what happens at pi. And so we're going to see this part of the curve repeat to the right-hand side. Okay, what if we want to extend this to the left-hand side? Well, again, let's see what the unit circle is going to tell us. By the way, if I extend just up to 1 tick mark, this is halfway between 0 and negative pi over 2. So this will be a negative pi over 4. So looking at the unit circle, here's my angle, and I want to open negative pi over 4 radians. That means I open clockwise, and I get an angle that is coterminal to 7 pi over 4. Where at this point, I'm going to have a negative radical 2 over 2 for the y value, so that means that sine is negative radical 2 over 2. So at negative pi over 4, we get about negative 0.7, so about here. Then what happens at negative pi over 2? Again, on the unit circle, here's my angle opening to negative pi over 2. That is coterminal to 3 pi over 2, and it has a y value of negative 1. So that means that sine of negative pi over 2 will be negative 1. So again, we're just going to see all of these values repeat. we're going to get an extension of the sine curve that looks more or less like this. And I want to describe the characteristics of this graph, and to do so we're going to need a few definitions. So I'm going to push this up a little so we can take a look at this box on the bottom left-hand corner. The first definition is for amplitude, and amplitude describes half the distance between the highest point and the lowest point on the graph. Okay, so this is half the distance between highest point corresponds to the largest y value. So between the largest y value and lowest, which would mean smallest y value, on the graph. And so we can actually write an equation for it. I'll let A represent the amplitude, and I'll say the amplitude is half the distance between the maximum y value, which I'm going to call y max, minus the smallest, so which I'm going to call y min. That's amplitude. So if we try to calculate amplitude for our graph, well, we said our maximum y value, the maximum y value we reach is a 1. The smallest y value we reach is a -1. So that means that the amplitude, let's go ahead and write this over on the bottom right hand corner. That means that the amplitude is going to be 1/2 times a 1 minus the smallest y value, which is a -1. So that is 1/2 of 2, because negative and negative become positive, so we get 1 plus 1, which is simply just 1. Okay, so this has an amplitude of 1. And I'm going to color code that. And I'll also label it on the graph. So again, the complete distance between the highest and the lowest point would be represented by this distance here. And if we think about how long that is, well, this is 1 unit and 1 unit, so together they make up 2 units. If I want half of that, then I only get 1. Okay, so the amplitude is just half that distance. By the way, I drew the amplitude here, but I might as well could have drawn it here and say, well, the amplitude is half the distance, so this is also half the distance, which means it's 1. That's amplitude. Alright, now period. Period refers to the distance along the x-axis that is necessary to complete one cycle. Okay, well, if I take a look at what is the x-axis representing, the x-axis is representing the different angles and different measurements of the angles. And from the unit circle, I already know that if I go from 0 to 2 pi, that is going to complete one cycle, right? So, in fact, you can verify that because after you complete the cycle, you're going to start to see the graph repeat, right? So after 2 pi, you're going to see this part of the curve, which corresponds to this part of the curve. So one unique one unique repetition happens between 0 and 2 pi, and that distance is 2 pi. So I'm going to label that, color code that green. Let's say this is the period of 2 pi. For short, let's call it P. This is 2 pi. Okay, and one more definition. That is the definition of zeros. So zeros refers to the points at which the graph touches the x-axis. Which I'll color code pink. So just by looking at this diagram or this graph, I see that 1, 0 happens at negative 3 pi, happens at negative 2 pi, at negative pi, at 0, pi, 2 pi, and 3 pi. So I can see that those points occur at multiples of pi, right? At integer multiples of pi. So the zeros are going to happen when x is equal to n times pi, where n is representing an integer. So it could represent 0, plus or minus 1, plus or minus 2, so on and so forth. Okay, and finally, domain and range. Domain and range are the same, have the same exact meaning as what you've learned for other graphs that you plotted in algebra. So domain refers to the set of all possible inputs. In this case, those input values are the x values, the angle measures. So for the domain, because there is no restriction on the graph, and we can plug in any x value that we want and get out a corresponding y value, we say that the domain is from negative infinity to positive infinity. And then for the range means all the y values, all the possible y values. Well, if I think about the range, there is a restriction, right? Like for instance, I never reach negative 2 on the y-axis. There's no angle that corresponds to a sine value of negative 2. In fact, nothing beyond or nothing below negative 1 is ever reached by the graph. So that means I have a lower bound on the range of negative 1. And here I'm using the bracket because bracket means that negative 1 is included, meaning we actually do reach negative 1 at some point. And then going up on the y-axis, we also have an upper bound. We don't ever reach any number beyond 1. The highest we ever reach is a 1. So the range will be from negative 1 to 1. And so for the sine graph, those are the main characteristics that we're interested in: the domain, range, amplitude, period, and zeros. We're now going to be graphing the cosine graph. And as you can see, the table of points has already been completed for us. They've plotted, they've evaluated cosine for 0, pi over 2, pi, 3 pi over 2, and 2 pi. And gotten these points 0, 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and 2 pi, 1. So the first thing that I'm going to do is plot these points. So first one is at 0, 0, 1, which is up here. Then we have pi over 2 comma 0, that's this point. Then we have pi comma -1, which is down here. Then we have 3 pi over 2 comma 0. And finally 2 pi comma 1. Okay. Now what we might be tempted to do is maybe draw straight lines between these to graph what would seem to be like a V, but we're not going to do that because we know that if we were to include pi over 4 as part of that table, and if we were to look at the unit circle to see what happens at pi over 4, at pi over 4 I would get a cosine value of radical 2 over 2, which means we have approximately 0.7. Alright, so we get approximately this point here. And similarly, if I take a look at what happens at 3 pi over 4, again, looking at the unit circle, here's 3 pi over 4. Cosine would be negative radical 2 over 2, which is about negative 0.7. So here we would get a point that's approximately there. And so just continuing to use the unit circle to help us find these other points at multiples of pi over 4, we would see then that the graph is not a V. We would see that the graph is actually curvy, just like sine was. So we get a curve that looks more or less like that. And that's what you want to be careful about at all times when you're graphing either sine or cosine. You're not ever going to have straight lines connecting the dots. It's always going to be some type of curve. Right, so let's use that one cycle. Remember, this is one cycle, 0 to 2 pi, completes one cycle. We're going to use that to extend the cosine graph. So I'll just transfer over what we got from the previous page, which were the points 0, 1, pi over 2, 0, pi, -1, 3 pi over 2, 0, and 2 pi, 1. And so we had this curve. Again, remember, we're not drawing straight lines. We always have curves. Just to simplify our work, I'm not drawing the other points at pi over 4 and 3 pi over 4, but basically I am trying to approximate that curve nicely. Now if we ask, well, what happens beyond that? What happens at, for example, 5 pi over 2? Well, here is unit circle. 2 pi would mean complete one cycle, and then if I add a pi over 2, okay, I'm going to end up at an angle corresponding to pi over 2, which actually measures 5 pi over 2. Okay, so what I mean by that is this angle that completes one cycle and then completes pi over 2 more radians is 5 pi over 2. So at that point, we're going to get a cosine of 0. So that means that this is going to be 0, which is repeating what happened at pi over 2. So you can see that these points are going to continue to repeat. At 3 pi, we're going to have a repetition of what happens at pi, which means we reach -1. This is somewhat like that. Going on to, extending on to the left-hand side into the negatives, at negative pi over 2, this is going to go down to 0. Then at negative pi, we're going to go down to -1. Then to at 0 to -3 pi over 2. To 1 at -2 pi. To 0 at -5 pi over 2. And to -1 at -3 pi. Again, you can verify all of these values by just looking at the unit circle. So like at negative pi over 2, that means that I have an angle that opens clockwise, pi over 2 radians. That corresponds to 3 pi over 2. And if we look at cosine, we get a 0, which is precisely what we're drawing here, 0. So now if we draw the curve connecting those points, we're going to see something more or less like this. And that would be the cosine graph. Now if we're looking at the characteristics, starting with domain, there is no restriction on the angle that we can plug into cosine, and x is representing the angle in this case. So that means that our domain is from negative infinity to positive infinity. As far as the range is concerned, that's referring to what are all the possible y values that are attained by the graph. Well, the graph has a minimum value of -1. It doesn't go beyond -1. So we have a lower bound of -1. And we also have an upper bound of 1 because it doesn't reach any y value beyond 1. So it just lives between -1 and 1, oscillating forever. Now, what about the amplitude? Well, amplitude is going to be exactly the same as for sine. If you remember, for sine, we calculate it to be 1/2 times the maximum y value, which is 1, minus the minimum y value, which is -1. And that gives us 1/2 times 2, which is 1. Okay, so the amplitude is still 1. What about period? How long does it take the graph before it starts to repeat? How long until it completes one full cycle, and then we start seeing repetitions of that cycle? Well, just like on the unit circle, it completes one cycle between 0 and 2 pi, right? This is where we see a unique part of the graph. After that, we start seeing a repetition. This part corresponds to this part. So the period is 2 pi. And finally, the zeros. Where is the graph touching the x-axis? Well, this is where it's different from sine, because we see zeros at -5 pi over 2, at -3 pi over 2. So basically at any odd multiple of pi over 2. The way that we would express that in an equation would be that x would have to be an odd multiple of pi over 2, so n would have to be a plus or minus 1, plus or minus 2, plus or minus 3, we're looking at odd numbers, plus or minus 5, and basically anything greater than that. So we want to be careful not to write 2, just like what I was about to do, or to write 4, because if n is 2, then we would have a 2 times pi over 2, which would end up being 2 pi over 2, and then the 2's would cancel out, giving us just pi. So we would be claiming that there is a 0 at pi, that it passes through the x-axis at pi. And, well, that's not true, right? It passes through the x-axis at pi over 2 and at 3 pi over 2. So this is one way of writing it. Okay, so I'm going to box this as one possible way, but the textbook actually adopts a different way of writing it, which I'm going to write down below. So, or the second way of writing it would be to say, well, x is 2n plus 1 times pi over 2, where n is equal to 0, plus or minus 1, plus or minus 2, plus or minus 3, or any other integer. Now let me explain why this works. Okay. Let's think about any even number. Okay, so this is just some side work, just brainstorming. If you think about any even number, what makes a number even is the fact that it can be written as 2 times something, right? Like for example, if I think about 10, 10 is an even number. 10 can be written as 5 times 2, right? So 10 is 5 times 2. If I think about, I don't know, let's say like 22, that can be written as 11 times 2. If you think about, let's say 36, 36 is 18 times 2. So in general, any even number can be written as an n, where n is representing any integer times 2, or just 2n. Okay, where n can be 0, plus or minus 1, plus or minus 2, so on and so forth. Now what we're trying to express is an odd number, right? We're trying to say an odd number times pi over 2. So if an even number is given by 2n, then if I add 1 to it, I'm going to get an odd number. Okay, so an odd number is represented by 2n plus 1. Now why is that? Well, think on the number line. The number line alternates between even and odd numbers, right? 0 is even, 1 is odd. 2 is even, 3 is odd. Okay, so we go even, I'll just write E for even, and then odd. Then even, and then odd. And that continues forever. If I go down to -1, that is going to be odd. So if 2n is representing an even number along this line, like for instance, let's say it's representing the 2, then adding 1 to that number will give me an odd number, right? So if 2n is even, then 2n plus 1 has to be odd. And so that's what's used here. This 2n plus 1 is the odd number. Okay, this is an odd number. An odd number times pi over 2, where n in this case could be anything. Could be 0, plus or minus 1, plus or minus 2, so on and so forth. So that is the notation that the textbook will use mostly, and as a result, it is the notation that the homework on my lab is going to be expecting. Okay, so make sure that you are comfortable with the second method of writing the answer. The next graph that we're going to be considering is the cosecant graph. And actually for the cosecant, I'm going to rely heavily on the sine graph, and here's why. If you recall, cosecant of x is the same thing as 1 over sine of x, because secant and cosecant are reciprocals of each other. So when I'm calculating what is cosecant at 0, for instance, I'm actually going to be plugging it into 1 over sine 0. So let's do that. What is 1 over sine of 0? Well, go back to page 1. Look at the first entry of the table. We said sine of 0 is 0. So this is 1 over 0, which is undefined. Okay, so maybe at this point we're not too sure what's going on here for that point. So we'll just draw a question mark and we'll come back to it to see if we can figure out what to do about that point. The next one is pi over 4. So I'm going to try to evaluate what is 1 over sine of pi over 4. Now if you recall, sine of pi over 4 was radical 2 over 2. So if I take the reciprocal of that, I'm going to end up with a 2 over radical 2, which if we punch into the calculator, 2 over radical 2 will give us approximately 1.4. So I'm going to plot the point pi over 4, comma 1.4, where again, this is an approximation. So over here on the graph, we're missing all of the tick marks that deal with multiples of pi over 4. So let's draw those in. we already know what they are. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and that would be the last one because then we have 8 pi over 4, which is 2 pi. Okay, so at pi over 4, we reach 1.4. So here's 1, this is 1.5. So 1.4 is going to be slightly below that. Okay, then what happens at pi over 2? Well, then we have 1 over sine of pi over 2. And if you take a look at pi over 2, sine of pi over 2 is 1. So here we simply have a 1 over 1, which is 1. Okay, so at pi over 2, we reach 1. Then at 3 pi over 4, again, we're considering 1 over sine of 3 pi over 4, which is going to be, well, at 3 pi over 4, we have radical 2 over 2. So this is going to be 2 over radical 2 when we take the reciprocal. That means that we have the point 3 pi over 4, comma, approximately 1.4. That's what we found when we're considering pi over 4. So we'll get this point that should be at the same level as the point at pi over 4. Then at pi, we have 1 over sine pi, which is going to be what? Let's see. Sine pi is 0. So we have that undefined again. Okay, so something is happening, but we don't know what exactly it is yet. Okay, then at 1 over sine of 5 pi over 4, if you look at 5 pi over 4, we're going to get the negative radical 2 over 2. So if you flip it to get cosecant, you're going to get negative 2 over radical 2. So that'll mean that we'll have point negative 5 pi over 4, comma, negative 1.4, right? Because 2 over radical 2 was 1.4, and if we have a negative, well, then we just prepend it with the negative. At 3 pi over 2, sine of 3 pi over 2 was negative 1. So that means that this will be a 1 over negative 1, which is negative 1. Okay, so at 3 pi over 2, and actually I forgot to plot this one, so let me plot this one first. So at 5 pi over 4, we have a negative 1.4. This is negative 1. This would be negative 1.5. So negative 1.4 would be slightly below it, or slightly before it, I should say, slightly above it. And then at 3 pi over 2, we reach negative 1. And at 7 pi over 4, we're going to take the reciprocal of negative pi over 2. So this, negative radical 2 over 2. So this is negative 2 over radical 2. That means that we're going to get a 7 pi over 4, comma, negative 1.4. So that'll be here. And finally, at 2 pi, we got sine of 2 pi is 0. So if we try to find the reciprocal of that, that is going to be a 1 over 0, which is undefined. Okay, so again, there's that question mark of what happens there. Okay, so in order to figure out what is going on, let's try to instead find something that is, or cosecant of an x value that is very close to 0, but a little bit greater than. So what I mean by that is maybe we can try to find 1 over sine of like 0.1, let's say. And 1 over sine of 0.1 gives me 10. So that would mean that very close to 0, I get a number that's very high up at least in the window of this graph at 10. Let's try to get a little bit closer. So if I do sine of, or 1 over sine of 0.01, then I get 100. And if I try to get even closer to 0, let's say 0.0001, we get 10,000. So what's happening is that as we come closer and closer to 0, okay, from the right-hand side, meaning we get something that is still greater than 0, but we get really close to 0, the graph shoots up because we start getting these very high numbers. And then as we go away from 0, we're going to start coming down to this value that we found of 1.4. And just to prove it to you, let's test something that's close to pi over 4 but less than it. So if I do pi over 4, that gives me 0.7853. So let's test what happens at 1 over sine of 0.78. Say. So that would be like 0.78000, which is less than pi over 4. Okay. So I get 1.421, which is going to be a little greater than what we had at sine of 1 over sine of pi over 4. So what we see then is a behavior like this. And then it goes down to that 1, comes back up to 3 pi over 4, and then something again weird happens at pi. Well, let's try and get really close to pi from the left-hand side, meaning we're going to plug in a value that is less than 3 pi over 4, less than pi, which is 3.1415, but is still less than, something that's close but less than. So for instance, I could try 1 over sine of 3.1415. And wow, that's a very large number, 10,792. If I try to get even closer, let's see what is pi. Pi is 3.141592. Let's see what happens if I have 1 over sine of 3.141592 with zeros after it. So I'm getting closer and closer to pi. That gives me 153, not even 1,530,011. So as we get closer and closer to pi, these numbers start getting larger and larger. Okay. But the funny thing is, we never actually have the graph cross this. If we were to draw a vertical line, it never crosses the vertical line passing through pi because it just continues to grow larger and larger, and then at pi it's undefined. So the behavior that we're seeing here is special, and we actually draw vertical lines at the places where the graph is undefined. These vertical lines attract the shape of the graph. Okay, so the graph will go towards those lines, but they never cross, and they're called asymptotes. Okay, so here, I'm going to label this asymptote. Let's see what happens as we get close to pi from the right-hand side, though. That means that I'm going to try to plug in a value that is larger than pi, but close to pi. So again, remember, pi is this 3.141592. If I want to plug in something that is slightly larger than this, I can try to plug in 3.142. Right, that's going to be a little bit larger than that, and then see what that gives me. And notice that's giving me a very negative number, negative 2,454. If I try to get even closer, so maybe if I do 1.1417, 6, because this is still larger than pi, but closer, then it starts to get more negative. Okay, in this case I have negative 136,120. So on the right of this vertical line, the graph is going to go down to negative infinity. And then it'll go and meet these points up to, it'll reach up to a maximum of negative 1. Then it'll go through the negative 1.4. And as we're getting close to 2 pi, which is the other place where we had undefined, we're going to get that the graph is going to go down to negative infinity again. Okay, again, we haven't shown it, but we can do so on the calculator. 2 pi is 6.2831. If I try to look for a number that is less than 2 pi, but still pretty close, I can plug in 6. Let's say 2800, right? That is less than that number, but close. And I see that we get negative 313. So if I try to get even closer, let's say like 6.2831, okay, it starts to get more and more negative. Okay. Right, so that's going to go down to negative infinity. Right, so the moral of the story is anytime you have undefined, you're going to have an asymptote. And that asymptote is going to attract the shape of the graph. So just to define it, an asymptote, this is going to be a line that attracts the shape of the graph. In the case of cosecant, it corresponds to places where the function is undefined. And in general, that's going to be true. If a function is undefined, then that likely means that, or not likely, you will have an asymptote at that x value. Okay, so in this case, we say x is equal to 0 is an asymptote, and x is equal to pi is an asymptote, x is equal to 2 pi is an asymptote. And what I want to do now is extend the cosecant graph. And instead of bringing over or copying over the one cycle that happens between 0 to 2 pi, I want to give you some tips that can help you graph this a little bit more quicker. You want to start by drawing the sine graph as reference. Okay, so what that means is, well, I'm going to plot 0, 0 because that is a point on sine, and then at pi over 2 we reach 1, at pi we reach 0, at 3 pi over 2 we reach negative 1, and then at 2 pi 0, and after that it repeats, right? So at 5 pi over 2 we go up to 1, at 3 pi down to 0. Going into the negatives, we go negative 1 at negative pi over 2. Then at negative pi we reach 0. Then 1 at negative 3 pi over 2. Then 0, negative 1, and 0. So what I'll do is I'll draw sine kind of dashed because, again, this is only our reference graph. This is not ultimately the graph that we're interested in. We're just using it to help us with cosecant. So that's the first step, draw sine as a reference. The second step would be to draw asymptotes that wherever we have zeros for sine. And now why would we want to do that? Well, remember, cosecant is a reciprocal of sine. So if sine has 0, so for instance here it has a 0, or at pi it has a 0, then 1 over that 0 is going to give us undefined. So that is going to correspond to asymptotes. That means that we have 1 here, 1 here, here, and same in the opposite direction. Okay, and then finally the last step. You want to flip, and here I'll use quotes, like you want to flip the shape of sine. The shape of the graph of sine, that is. Okay, so what I mean by that is if you have between 0 and pi the shape of the graph going downwards, then we're going to flip to create an upwards parabola that has the vertex at 1. If you have the shape of sine facing upwards or going up, then we're going to flip that and make a downwards facing parabola for cosecant. Okay, so ultimately what we get is the following. Okay, so what are the characteristics of cosecant now? Well, as far as the domain, we have to place restrictions because there are places where cosecant is undefined, and we don't ever want to have x values that cause undefined y values as part of our domain. So that means that in the domain, we'll have everything from negative infinity to positive infinity, except the places where we have multiples of pi, because at multiples of pi we have asymptotes. Okay, so except where x is equal to n times pi, where n can be any positive or negative integer or 0. What about the range? Well, the range is a little different now too, because, well, before we had a minimum y value of of negative 1, a maximum y value of 1. That is no longer the case, right? Now we can get very negative y values, and we can also get very positive y values. So the graph can extend all the way down to negative infinity, but it can also go up to positive infinity. The only place in the along the y-axis, or I should say the only y values that are never touched by the graph, is y values between 1 and negative 1. Right here we see a little strip where there is nothing that touches the cosecant graph, right, in this area here. So for the range, we're going to say we can have anything between negative infinity up to negative 1, right? The graph can touch any place from negative infinity up to negative 1. But after that, there is nothing until we reach 1, and then out to infinity, we start seeing the graph again. So because we have two disjoint areas in which the graph exists, we actually use union. And this is a symbol that was introduced in your algebra courses when you have two places that do not overlap, that are part of a solution set, we use union. In this case, it's not necessarily that it's part of a solution set, it's just part of where we see the graph on the y, if we're considering y values. Okay, what about amplitude? Well, amplitude would mean half the distance between the maximum y value and the minimum y value. But in this case, the maximum y value is never attained because this goes on to infinity. Same thing for the minimum y value. That is never attained because it goes down to negative infinity. So the amplitude here does not really apply. So we just write NA. As y max is infinity and y min is negative infinity. We don't actually reach any number. What about the period? When do we start seeing this graph repeat? Well, if I start looking from 0 on to the right, I see an upward parabola followed by a downward parabola. That's not repeating yet because these two are different. And then followed by upward parabola. So this is now a repetition of this part of the graph. So between 0 to 2 pi, that is where we see a unique part of the graph, and then after that we start seeing repetitions going in both directions. So that means that the period is 2 pi, just like what we had for sine. And that is always going to be true. Whatever we have as the period for sine will also be the period for cosecant. What about zeros? Does this graph ever touch the x-axis? Well, the answer is no, because the graph is only these parabolas that either face down or face up or open down. So we never see them cross the x-axis. So actually we have none here. We don't have any. And finally, we have asymptotes. Asymptotes are present. They happen wherever sine has zeros. So those would be at multiples of pi. Okay, so the asymptotes are going to be given by x is equal to n pi, where n could be 0, plus or minus 1, plus or minus 2, so on and so forth. The last graph that we're going to be considering for today's lecture is the secant graph. And as you can see here on page 7, one cycle of it has already been given to us. In this case, they plotted points 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the way those are being computed is by considering the cosine graph, because secant is the reciprocal of cosine, so we might as well use it to help us graph secant. So for 0, we get 1 over cosine 0, which is a 1. So 1 over 1 will give us 1, which means that we have to plot the point 0, comma 1, and that would be this point here. The next point they consider is a pi over 2. 1 over cosine pi over 2 would be 1 over 0, because cosine pi over 2 is 0, which is going to give us undefined, and that gives us an asymptote. Then at pi, we have 1 over cosine pi, which is 1 over negative 1, and that simplifies to simply negative 1. So the point pi comma negative 1 would be here. Then at 3 pi over 2, we're going to get another asymptote, and at 2 pi, we're going to get 1. Now, of course, these are not enough to draw completely these curves. I mean, there's no way that we can deduce that this curve is going to be the result of that point. So, of course, there are other points that you can plug in, other x values that you can plug in into 1 over cosine x, and ultimately it is going to give you this, this shape. Now, just so that we're consistent with what we used to label the graph of cosecant, I'm going to draw the asymptotes in a dotted blue highlighter because that's what we use for there. And these graphs then, these parabolas are now, or half parabolas in the case of these two, are going to be the graphs of secant. So let's extend that. And we're going to use that same tip that I gave you guys for the graph of cosecant, meaning we're going to start by drawing the reciprocal function as a reference. Now for secant, the reciprocal function would be cosine, so we'll draw cosine first. Cosine passes through the point 0, 1, pi over 2, 0, pi, -1, 3 pi over 2, 0, and 2 pi, 1. That's one complete cycle of cosine. And from there it repeats. So at 5 pi over 2 we reach 0, and then at 3 pi we reach -1. Same going in the negative direction. Negative pi over 2 we reach 0, then -1, then 0, then +1, then 0, then -1. So it looks something like this. Okay, so that's the first step. The next step is to draw asymptotes wherever we have zeros for cosine. So we have a 0 at pi over 2, at 3 pi over 2, at 5 pi over 2, at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. And then the last step would be to flip the shape of the reciprocal function. So for instance, between negative pi over 2 and pi over 2, I have downwards facing cosine. So that means that secant will have an upwards facing parabola in that interval. Between pi over 2 and 3 pi over 2, we have an upwards facing part of the graph. So that means that we're going to flip it and get a downwards parabola. And so that same principle is going to apply. What you have to be careful is to never have the graph cross the asymptote, because then that means that you actually attain a value at 3 pi over 2 for secant. And we know that that doesn't happen because at that point we get undefined. Okay, so we'll just draw these parabolas, making sure to not cross the asymptotes. Right, now let's look at characteristics. Domain. Well, it's going to be all of the real numbers except where secant is undefined. So from negative infinity to positive infinity, except, well, the places where it's undefined is at these zeros. So except when x is equal to an odd multiple of pi over 2. Okay, so remember, odd number can be represented by a 2n plus 1 and then times pi over 2, where n would be 0, plus or minus 1, plus or minus 2, so on and so forth. Now what about the range? Well, range again is the y values that are reached by the graph. We go all the way down to negative infinity, and then if we want to see what is the highest y value, well, there's a momentary break. Okay, that happens at -1, because from -1 to 1 there's no part of the secant graph. So we go from negative infinity to -1, and then the graph reappears at 1 all the way up to positive infinity. Okay, so don't forget to include the union between those two disjoint ranges. But this is basically saying we can find the graph anywhere between negative infinity to negative 1 or between 1 to positive infinity. The amplitude will not apply here, just like it didn't apply with cosecant, because we're trying to find the difference between y max and y min, and y max is infinity, y min is infinity. It's not actual numbers, so we can't subtract anything that is not a number. For the period, we want to see where does the graph repeat. Well, again, think about it just between 0 and 2 pi. That was the original cycle that was given to us. That is where we see a unique part of the graph. And then if you start considering this half of the parabola that comes after 2 pi, that corresponds to this half of the parabola that comes after 0. So we start seeing a repetition after 2 pi. Now, if that's a little bit difficult to see, you can also instead consider two whole parabolas. So meaning I could consider the interval between negative pi over 2 and 3 pi over 2, and then see what the distance would be between those two numbers. So if you want to do that instead, what we could do is take 3 pi over 2 and subtract away this negative pi over 2, and that would give us 3 pi over 2 plus pi over 2, because negative times negative becomes positive, which is going to give us a 4 pi over 2, which is 2 pi. Okay, so ultimately the period is 2 pi, whichever way you decide to consider the cycle. Okay. Does this graph have zeros? Does this graph touch the x-axis at any point? It does not. And finally, where do we have asymptotes? Well, we have asymptotes at odd multiples of pi over 2, which is the same as the numbers that we excluded from the domain. So one way to find asymptotes is to always look at the domain and see what was excluded. We excluded the 2n plus 1 times pi over 2, where n can be 0, plus or minus 1, plus or minus 2, or any other integer. And so that concludes our lecture for today. And next time that we meet, we'll be considering the remaining trigonometric functions and their graphs.